So we're very happy to have Bruno Valeixo Bento from IFT to talk about zeta hunting on the Riemann-flat landscape. Thank you. Take it away.
Thanks a lot. Thanks to all of you who are here to listen to our talks and to the organizers, of course, for making it happen. Today, I want to tell you a little bit about the work I've been doing with Miguel on Riemann-flat compactifications, and in particular, compactifications where you use Casimir energies and fluxes to try and get de Sitter solutions in lower dimensions. So let me start right away by spoiling the results so that you know what you're here for. The first thing I want to show you is our five-dimensional M theory maximum. I will work our way towards this solution in a few slides. And this is a solution that we find on Riemann-flat manifolds with Casimir energies and fluxes. The second thing I'm going to show you, and I'm going to spoil right away, is the set of no-gos that we found in our recent paper based on this setup. So just from the fact that you assume the only ingredients you use are fluxes, Casimir, and Riemann-flat manifolds, you can prove a set of no-go theorems that pinpoint which de Sitter solutions you can or cannot find in this kind of setup. So by the end of this talk, I hope that these two things are clear and make sense to you. So let's work our way towards this. The first thing I need to mention, of course, is the de Sitter problem. This hard problem of hunting for de Sitter in string theory. We are probably, most of us at least, very familiar to these discussions. Some of the results that this difficulty go all the way back to the 80s with Dine and Seiberg showing that you cannot fully go to the asymptotics and find solutions there. But then you have results like the Maldacen and Nunez theorem that tell you if you want a de Sitter solution, de Sitter minimum in supergravity theories, then you need some kind of negative energy source. Which you can find in string theory, but not in field theory. And so these are all clues that we've been gathering along the years that tell you which kind of thing you should look at if you actually want a de Sitter solution. We've seen some proposals as well, like KKLT and LVS that Andrea just mentioned. These constructions are very complicated in the sense that they need to include a bunch of ingredients that are hard to study, like orientifold planes, D-branes for the uplift, fluxes as the ones we're going to use, but also typically these constructions have warping, which was one of the main focus of the talk we just listened to. And they include perturbative and non-perturbative corrections that are typically very hard to check. If you want to know whether these things are well under control, it's very hard to do this explicit in these constructions. So we can ask ourselves what kind of negative contributions we could use and try and simplify a little bit this type of constructions. So the examples I mentioned before, like KKLT and LVS, typically use orientifold planes as your negative source of energy. And these are hard because they are very stringy. If you want an understanding at the level of field theory, you find trouble treating this perturbatively. Another source, the one I'm going to use here, is Casimir energy. These are basically vacuum energies. You get vacuum Casimir energies when you break SUSY, and you have this SUSY, non-SUSY background with non-trivial boundary conditions, which generate some sort of vacuum energy. It doesn't vanish. And this is the kind of thing that you can compute explicitly in field theory. If you know the stringy origin, you can also do this kind of computation. It's a higher loop computation in string theory, and then take the supergravity limit and compare. If you don't, you can just do it at the level of the field theory and then argue whether this is controlled or not. We'll get there in a sec. But this is the kind of contribution that has been used in some constructions in the past. So here I will refer to this work by Bruno, Eva, and Gonzalo on hyperbolic compactifications of M theory. Here they use exactly this kind of construction. They have fluxes, they have Casimir energies. In their case, because they are compactifying on hyperbolic manifolds, they also have curvature. And they put all of this together. In particular, they also have warping in their construction. And they find the de Sitter 4 in M theory. So one thing about this construction, although it is very nice, is that it's still a bit hard because working with hyperbolic manifolds, and in particular evaluating Casimir energies on these hyperbolic manifolds, is everything but trivial. And so Miguel and I wanted to go for something a little bit simpler. And so we asked ourselves, what kind of things do we know well? What kind of things do we trust the most as physicists? And we will argue that the kind of things that we like as physicists are circles and symmetries. If you give a physicist a circle and the symmetry, you have a happy physicist in most cases. So a concrete example would be, for example, the orbifold of the circle. So you consider the symmetry or you identify points in this way, in some sort of reflection. And the endpoint of this identification, or the result of this identification, is this orbifold that you can think of as S1 mod Z2, which is effectively an interval. This interval, if you look at it, has one thing that we don't particularly like, which are the fixed points. These correspond to orbifold singularities, which have their own subtleties to take into account. And so we wanted something even simpler than an orbifold. And that's what leads us to Riemann-flat manifolds. The basic definition of a Riemann-flat manifold is, or in other words, the most general Riemann-flat manifold can be constructed in this way. You take a torus, which is just many circles, effectively, and you mod it out by a subgroup of the isometries of the torus. This group must be freely acting. And this is what's going to lead us to the no orbifold singularities point that I was referring to. It's going to get rid of any fixed points that you might be worried about. The action of this group is in the form of this sort of identification, where you take a coordinate on the torus, you perform a twist on this coordinate, and then you shift by some constant vector. So all elements of this group are of this form. They act in this way. And they act in this way without any fixed points. So apart from the no orbifold singularities point, there are two other things that are very nice about Riemann-flat manifolds. One of them is that they have generically less moduli than the original TK. So if you consider the TK before the identifications and you compare the number of moduli with the one for the Riemann-flat manifold, the Riemann-flat manifold usually has less moduli. And this is nice because it's less things you need to worry about and to stabilize. The second thing, which is very nice about Riemann-flat manifolds, is that the Casimir energies come enhanced when compared to the torus without identifications. And so this helps you get a stronger contribution from Casimir energies, which is good for control of your solution at the end of the day. So let me give you an example, which is probably familiar to many of you, the Klein bottle. The Klein bottle can be seen as a Riemann-flat manifold. To identify x with minus x, which is similar to the orbifold picture I showed you in the previous slide. But together with this identification, we are going to shift along the y coordinates. And this is what gets rid of your would-be fixed points. In this language, in terms of a shift matrix, twist matrix and the shift vector, the Klein bottle is written in this form. So there's a matrix, there's a shift vector, a constant vector, and it just realizes this identification. We'll come back to the Klein bottle a bit later. So what are we going to consider for our potential de Sitter solutions? We want a scalar potential, which gets contributions only from fluxes. So you have flux terms and a Casimir contribution. Because we want this Casimir contribution to be negative, this is supposed to be our negative source. We are imposing this minus sign and then working in terms of this coefficient C. We want to choose cases where this coefficient is positive. In general, the kind of potential you'll get is like this black line, if you're successful at least. And it will be a combination of fluxes, the red lines, and Casimir energy, the blue line. And the very nice thing about Casimir energies on Riemann-flat manifolds is that you can actually compute them explicitly. We have worked out what these Casimir energies are. We can give you the Casimir energy for any kind of field. So this factor here takes into account the representation. It could be a scalar, a graviton, a vector, a fermion. If it is a fermion, let's say a spinor, you can also take into account non-trivial boundary conditions. So you could, for example, flip or twist the boundary condition for the spinor, and that's encoded by this phase factor. And you can compute it explicitly as a sum over the full lattice. So all the points identified by the torus, all the points identified by your group, the RFM group. And the propagator that you see here is basically the scalar field one. And of course, if you want the lower dimensional scalar potential, then you have to integrate over the compact space. So this is very explicit at the end of the day. One of the key results in our paper from July is that the integral part can be computed exactly in every case. At the end of the day, your Casimir potential is given as an infinite sum over some lattice, but it's an infinite sum over a sublattice of the full space. And the sublattice is the sublattice which is invariant under these twists. This is very good because at the end of the day, it means that you don't have to take care of the integration numerically, which can be very slow. And after you perform the integration, these sums are typically lower dimensional as well. So if you want to do this numerically, which we do, it also saves you a bunch of time in the numerical computation of the sums. The third reason why this is very nice is that it gives you a physical interpretation of what's going on. And this physical interpretation comes in terms of what we called Casimir brains. These Casimir brains are clumps of Casimir energy. And these clumps are precisely they correspond to these d-invariant subspaces, the subspaces we are summing over. And we can see this very explicitly in simple cases. So let's give the Klein bottle as an example again. What are the Casimir brains in this case? Well, because we have this explicit expression, you can look for the space, so the subspace of the RFM, where this contribution will be the largest. And because under the integral, everything is a constant, apart from these two terms, you'll get the largest contribution when this is the smallest, basically when the two terms cancel each other. In practice, this corresponds to the shortest distance between a point and its image. If you visualize it, this is what's happening in practice. The subspace that it corresponds to is what we call the Casimir brain. For the Klein bottle, what you're doing here is finding the points on the torus for which x is the same as minus x. Those will be x equals 0 and x equals 1/2. And that's exactly where you find the Casimir brains. Because we have the expression for the Casimir energy density, you can actually just plot the Casimir energy and confirm this expectation. And the expectation is that each of the terms will be effectively a Casimir brain that gives you all the things you need to know. It's basically the whole contribution that you need. Let me plot it to show you that this is actually the case. This is the Klein bottle again. You'll see that the Casimir energy density peaks at 0 and 1/2, exactly the position of the Casimir brains, which I'm showing here again in red. But then you can consider other examples. For example, this T3 mod Z3 is especially nice because it was considered in this paper as well. And so we can compare our results with their results. And once again, you see that the Casimir energy density peaks in very specific points. In this case, in these 3 points. And these are exactly the Casimir brains for the T3 mod Z3. So as soon as you know the Casimir brains, you know what the Casimir contribution will be to the potential. So now I'm finally in a position to show you our 5D maximum. It is a DS5 in M theory, compactified on a T6 mod Z8. So this particular RFM that we are considering is a quotient of the 6 torus, where our group is this Z8, which acts in a particular way. So first of all, this Riemann-flat manifold only has 5 moduli. So out of the 21 that the torus would have, 16 are projected out by the quotient alone. So we only have to deal with 5. In terms of the Casimir brains I was telling you about, in this setup, we get 2 Casimir brains, which are 2-dimensional. So these are 2 Casimir brains that wrap a T2, which is part of this Riemann-flat manifold. The value of the potential at the critical point, so at the maximum, is 10 to the minus 15 in 5-dimensional Planck units, which means there's a very large separation between this 5D Planck scale and the value of the potential. And you can also look at the size of the overall volume, which is the R modulus that appears in the potential I showed you. So in this case, it's 16 again in 5-dimensional Planck units, which you can use to look at the scale separation between the 11 and 5D Planck scales. But you also should worry about the smallest cycles, because the overall volume can be very large, but if it's very anisotropic, you could have a very large cycle and a very small cycle. So it's important to go and check what the small cycles are. In our particular case, the small cycles are these two correspond to these two values, and they are still larger than the 5D Planck scale. You can use this to estimate corrections and to check that the corrections are under control for our solution. And finally, because you have a way of computing the energy densities everywhere, you can look at the average energy density and use this as an estimation of how much higher curvature corrections or higher loop corrections would affect the solution that we find. In this case, we can think of this parameter epsilon as an expansion parameter, which is basically correcting the perfectly Riemann-flat solution in terms of the fluxes and Casimir contributions that you're adding. And as you see, 10 to the minus 10 leads to a very controlled case or situation. Okay, very good. So this leads us to the second thing that I spoiled at the beginning. In our most recent paper, we took the same exact setup. So once again, flux contributions and Casimir contribution. And we studied basically we asked what kind of things should you expect? What kind of solutions can you actually find in this setup? And the second good thing, so one of the good things of RFM compactification is that you can do everything very explicitly. The second thing is that these compactifications are so simple in like conceptually, that you can say a lot about what's ruled out even before you work out the details. Let me be more precise. For the flux contributions, you know exactly how the flux terms scale with the volume. It just depends on the P of the P form flux. For the Casimir energy, you also know exactly how this term scales with the volume of the compact space. And just by putting these two things together, you can conclude, for example, that if you start with a capital D dimensional theory, you will never be able to find a de Sitter minimum unless you satisfy this constraint. And this is very constraining, because if you start with supersymmetric theories, this can be at most 11, which means that little d could be at most 5. And that already excludes everything above 5. In fact, if you are a little bit more careful, you can also exclude 5, because you'll see that the only 11-dimensional theory that you could use doesn't have the right form of flux. And if you are even more careful and detailed, you can exclude DS4 as well. The DS4 case is a bit more involved, because you have to go theory by theory, studying what type of flux you have, what moduli the theory has, and then check whether this can be done or not. Let me be more concrete. The minimal requirements that we impose are that you have the fluxes that you need for this form of the potential. So you need a P1 and a P2 form flux to do this. And you need to make sure that there are no d-dimensional moduli that cannot be fixed. We are going to say that something can be done in principle if you have the ingredients to do it. We are not going to show that you can do it. We are not going to give you a specific solution. But if it could in principle be done, we cannot rule it out. And that's what we're going to say. Here's an example. Let's say you want to get a DS4 from type 2A. Type 2A is a d-dimensional theory. You want to go down to d equals 4. From the conditions here that I was arguing for in the previous slide, you know that we need an F6. Type 2 is nice because you do have an F6. So this minimal requirement is satisfied. The problem with type 2a is that you have to say to check the second minimal requirement. And in type 2a, you do have a modulus, the 10D dilaton, which cannot be fixed because you don't have enough terms in the potential to fix this modulus. You could try the same in type 2b. And again, you start in d equals 10, you go down to d equals 4, but now you don't have the f6. And so type 2b is excluded right away. Since I'm going a bit slower than I planned to, let me skip what I was going to say here. I can come back to it if it comes up in the discussion. So in the paper, you'll find two tables like this, where you summarize all these results. So the two examples I gave you are these two, so they're excluded. In fact, you can check that all the DS4 cases are excluded, they are ruled out. But then if you analyze the same two cases, type 2a and type 2b, in the case of the DS3, these can no longer be ruled out. And that's because you're allowed to turn on more fluxes. These fluxes could, in principle, stabilize the dilaton and the volume modulus. And so you cannot rule these out right away. So DS3 are possible in principle. The same applies for theories with 16 supercharges. Here are just the 32 supercharges cases. And we summarize all of this and explain all the details in the paper.
You have around 5 minutes left.
Thank you. So, okay, let me end with a fun observation. I just told you that the CETR 3 are not ruled out. In principle, you could find them. But one thing is to say that you can find them in principle. Another thing is to actually find one and do it explicitly. So the question is, how can you find them? Some of you might recognize this plot. This is a plot obtained in the CFT bootstrap program. And in fact, it corresponds to an island where you can find the 3D Ising model, so a specific CFT. And what we argue is that finding the CETR minima is very similar in essence to finding CFTs that satisfy all the CFT properties. And here's why. So let's go back to the scalar potential that we have. So again, we have our flux terms, we have our Casimir terms. If you want to find a critical point with the potential at the critical point equal to V0, these are the equations that you need to solve. So in order to do to think of this map, to think of this relation to the CFT bootstrap, what you can do is to think of these potential terms as the variables themselves. So you replace your moduli phi I and r by the terms in the potential, and you put them together in a vector that should be positive. So if you look at the way we define things, so this comes back to what I was emphasizing at the beginning, that we take out the minus sign. This should be a positive vector. And we want or values for this vector that are positive and satisfy the critical point conditions, which if you look at them a little bit, you'll see that they are just linear relations for linear equations for this vector V. So we could write it like this. What we want to find our critical point solutions is to find a vector V that satisfies this constraint. This is just a critical point. If you want the critical point to be a minimum of the potential, you also need to impose that the Hessian matrix at this point is positive definite or semi-definite, depending on how strict you want to be, allowing for flat directions or not. And so the problem you need to solve in practice is find which values of the moduli allow for some vector, which is positive, satisfying these constraints. If you know a little bit about the CFT bootstrap, this might ring a bell. In the CFT bootstrap, instead of moduli fields, you have scaling dimensions of operators. Instead of this vector of positive potential terms, you have these 3-point couplings or OPE coefficients. And instead of the DS critical point conditions, you have crossing symmetry that your CFT should satisfy. And the same way that I was identifying the 3D Ising model on that plot before, you can also think of a particular RFM compactification of a particular theory as a point on this region of parameter space. And so what we can do is we can reuse the semi-definite programming that people have been using in CFT Bootstrap to find optimal solutions, where optimal could mean the largest volumes or the smallest vacuum energy, satisfying these constraints. So to finish very quickly, let me just show you the toy example that we give in the paper. This is a toy model of M theory compactified on an 8-dimensional torus. Where we restrict the metric to only depend on two moduli so that you can do the analysis in an easy way. And these are the plots that correspond to the CFT one I showed you before. So the colored regions are allowed, the white regions are excluded. So any concrete RFM compactification given, for example, by these red points is excluded, is not allowed. If they overlap, then this is possible. It's not, you don't show that it's there, but it's allowed by these constraints. And you see that if you start turning off some fluxes, these regions start shrinking and the overlap might simply disappear. If you have questions, I can come back to these plots. I realized it was a bit quick, but let me just flash out the conclusions and move on to the discussion. So I wanted to leave you with these things. So one is we can compute Casimir energies very explicitly on RFMs. We can interpret these Casimir contributions as Casimir brane tensions. And you can show a bunch of no-go results just from the simple setup that we are considering. And in particular, this leads us to this very nice map between the search for DS vacua and the CFT bootstrap, which is nice if you want to reuse the methods that people have been optimizing for the CFT bootstrap in the search for the sitter vacua. So thank you, and be free to ask any questions you have.
All right, let's thank Bruno for the very nice talk. Is there any question from the audience? Michael?
So I had a question. These are both very good talks and very interesting. I had a question for both speakers actually, but the last speaker in particular. So when you have these, you neglected the orbifold points by using these, these special spaces, Riemann-flat, but they didn't have the orbifold points. But sometimes it's interesting to have the orbifold points. For example, you can get gauge groups and things like that generated at the orbifold points. Like for example, in the M case, you get the EA cross EA and things like that. You can get gauge groups that are might be interesting for granulification. But that would affect some of your calculations. So you would have like additional from the field strength for the gauge group, you would have additional positive contributions, and then from the Casimir contribution, you might have like Wilson lines or something which could affect the Casimir calculation. But anyway, it might affect your conclusions as well. I don't know. Did you consider those? I know they're more complicated.
Yeah. So that I agree. It's true that including these orbifold points would change the analysis. We'd have to be careful about those particular points. In principle, some of our methods might still be very useful to compute the Casimir energies in those cases. But we didn't look at any particular construction which includes orbifold points. So I cannot say anything which is much more concrete than this. But I agree that it would definitely be interesting to look at those. And try to take them into account without changing the story too much.
Right. And also physically, it's important to have these gauge groups, for compactification at the end.
Yeah.
And I don't know, is the previous speaker still there? Because I had a similar question for him. But Andreas.
Yeah. Maybe I should comment on that after.
Okay. That sounds
the question session for when the recording is stopped. Yeah, I'm happy to comment on it, but I think there was another question for the second speaker. So
right. Thank you.
Isn't?
Yeah, thanks for the talk, Bruno. I was wondering about something that you said when you were discussing the sitter 5 maximum and the validity of the solution and so on. So you mentioned that you looked at these at these different cycles and the sizes, and that they are, well, not particularly large, but maybe large enough in 5D Planck units. But I was wondering, don't you need to compare that with 11D Planck units? Like in string theory, when we do this, then we usually trust the compactification if it's large in string units, because you don't want winding modes to be too light. So I was wondering if you would compare it with 11D string with 11D Planck units over here, don't you then run into trouble? With like light M2 brains or M5 brains? I don't know.
A good question. I might be. Yeah, no, yeah, you're right. I think I should be talking about 11D. So these things are in 11D Planck units. I think I just wrote the wrong thing there.
Okay.
I think I just wrote the wrong thing there and I didn't notice. Because yeah, these volumes are expressed in 11D Planck units. So you're absolutely right. We should use 11D. If I'm not confusing myself right now, you should use the 11D. So the size of the cycles in 11D Planck units to estimate the corrections to the 11D
Yeah.
theory.
Okay. Okay.
Yeah.
Okay.
For
Good.
sure. Thanks a lot.
Okay. Thanks.
Just yeah,
Thanks.
exactly. Yeah, exactly. Sorry. So yeah, good clarification. I'm giving you the values in 11D Planck units, and I wrote 5D Planck units, and I didn't notice. Thanks a lot.
Okay. Okay. Thanks.
All right. Let's thank our speakers again today, and we'll rejoin for another talks in 2 weeks. Oh, sorry, Sab has a question, but let's first close the floor
Yeah.
and then make it into the offline discussion. And if you want to stay long, just